Hi, welcome to an audio test session with APx. These videos provide worthwhile information for APx users and demonstrations on a range of audio measurement applications. In this session, Dan demonstrates measuring MEMS microphones using the multi-input feature in APx500 software.
I'll go ahead and add my acoustic response measurement. And you'll notice that this now has results for both inputs. So there's an impulse response for the transducer interface and an impulse response for the PDM interface. There are essentially twice as many results, one for each input. So what I'll do here is I'll put in my desired stimulus level. Now keep in mind, at this point I've only calibrated the speaker for its output level at 1 kilohertz. So this is going to give us 94 dB SPL at 1 kilohertz, and outside that range we'll just see the speaker's natural response. Let's do a 2.5 second sweep, and we can go ahead and run the measurement. So here I have the impulse response of my reference microphone. Here is the impulse response of the two PDM microphones. And if I scroll through the results, here is the, I'll say, uncorrected frequency response of the speaker as measured by the measurement microphone. And here is the frequency response of the PDM microphones. Now normally what I would do at this point is equalize the source speaker, but again with our new sensitivity result I can do something a little bit more interesting. Again, I'll do a derived result, and again I will select sensitivity, and now what we get is the frequency response of the PDM microphones with respect to the measurement microphone. And again, it essentially divides out the effects of the source speaker. So even though the source speaker is not perfectly flat, or even very close to flat at 20 hertz or 20 kilohertz, I can clearly see the frequency response of these MEMS microphones, including their cavity resonance up at 15 or 16 kilohertz. Next, what I'll take a look at is transfer function. So we'll start out in transfer function, and in many ways it's going to be similar to acoustic response, but here actually instead of setting a derived result, I'll say that I want to generate the transfer function directly by reference. So the reference now, instead of being the generator, will be an input channel, and I'll say the reference is going to be the transducer interface. I don't need any match because these are both closed loop measurements. Time alignment will be relative to the reference. And let's go ahead and do 48K FFT for 1 hertz resolution. And let's do 31 averages with 50% overlap. What's interesting about transfer function is two things. The first is that I can get the transfer function in both magnitude and phase. So here we're looking at the magnitude response of the measurement mics with referred to the measurement microphone, but then I can also look at the phase response. So here is the phase of the MEMS microphones relative to my analog reference microphone. Now, one thing that's important to look at when you make transfer function measurements is the coherence result. So one way to think about coherence is it's the signal to noise ratio of the measurement itself. And one thing to be aware of is that the speaker doesn't give us perfectly even energy. It has its own frequency response. So particularly at 20 hertz, we can see that the coherence falls below 50%, and that definitely influences the quality of the measurement. But what you can clearly see is, say, between 80 or even 100 hertz, and even somewhat above 10 kilohertz, we have perfect coherence, so the quality of the measurement in this range is very high. Now, probably the primary use of transfer function is actually so we can make measurements not using a test signal, but perhaps using music or speech. So let's go ahead and do that. I'll change the waveform type from noise, and I'll select a file. I happen to have a collection of IEEE real speech signals. So let's say male model, and we'll do this measurement. And let's fire this off. So here it's interesting looking at the transfer function because we can see the test signal itself doesn't have energy across the full band because it's an actual speech signal. So there's mostly energy in here above 60 hertz and maybe to 8 or 10 kilohertz if we're stretching it. But nonetheless, we can still get a magnitude response and a phase response within the range in which we have good coherence. Anyway, that's a quick look at two topics. Number one, measuring MEMS microphones with acoustic response and transfer function, but especially using our new multi-input and sensitivity function in APx500 version 6. Thank you very much.
Thank you for joining us for this audio test session with APX.